Welcome everyone, thank you for being here. Warm welcome to you. Get yourself ready with a notebook, grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today you might want some graph paper. You can take the opportunity to sketch a graph, but you don't have to. This is about constructing a rational function. And this is really going to give us a chance to explore whether or not you understand some of the features of a rational function and how you can see those features in an equation, because we're going to have to create the equation. Okay? So the goal here is to construct a rational function that meets the following conditions. We have no vertical asymptotes. That is very important. We do have a horizontal asymptote at y equals 2. There is a hole at x equals 3. And really important that this function is only undefined at one point. There are not multiple points of discontinuity. So if you'd like to give this a shot for yourself, maybe take about 7 to 9 minutes. See if you can come up with a function that fits these conditions. And if you can graph it, feel free to take extra time to do that. Or if you would just like to check your proposed function, maybe go on Desmos and plug in your equation and see if that satisfies the conditions. So you can pause the video, go ahead and give yourself some time to do that. And then when you're ready, come on back, see how we do it here. Okay, in order to get started with this, we're actually going to take a look at some of the features of the graph of a rational function. That way, we're all on the same page here. In case you forgot, we can just review these briefly. One of those features, the vertical asymptote, it's one of the main features that students expect to see after they're introduced to the rational function, because the parent function, 1 over x, has a graph which looks something like this, and it's the first time we see this random vertical break in our graphs. So that sticks with us, right? So we really learn how to identify vertical asymptotes. They become very clear for us to see. And then we sort of start to expect to see them. Not every rational function has a vertical asymptote. We do have a vertical asymptote anytime we're approaching dividing a non-zero number by 0. So an example of that, in the rational case, f of x equals 1 over x. If x gets very close to 0, the values approach 1 divided by 0, which obviously doesn't make sense. It goes to infinity. It's kind of why we see this graph go up to infinity. And from the negative side, if x is a negative number that's still approaching 0, 1 over that approaches negative infinity. And that's kind of the defining feature of a vertical asymptote, is that on both sides of this boundary, the graph is sort of going off to the infinite. Sometimes both sides are going to the positive, sometimes both sides are going to the negative. But if there's a boundary that behaves in this sort of way, where the sides go to infinity, then we have a vertical asymptote. And what to look out for, this little purple arrow, what to look out for? Well, what you're looking out for is you're looking for factors in the denominator that are equal to 0. There's a bit of a caveat to that, but I'll get to that in a moment. So just focus on when factors in the denominator could possibly equal 0, and that could possibly give you a vertical asymptote. Okay. Now let's talk about the counterpart, the horizontal asymptote. The horizontal asymptote, it's like a horizontal boundary, but it's really important to remember that it only applies to the ends, like the left and the right sides of the graph. So that's when x itself is approaching positive infinity or negative infinity. Whereas the vertical asymptote is a result of the y values going to positive or negative infinity. The horizontal asymptote, it arises from when x is going to positive infinity or negative infinity. So we're only looking at the ends. Let's go back to the 1 over x graph just to show that. This horizontal boundary, which is pretty much overlapping the x-axis, it's really only imposing itself as a boundary like at the end, as we go all the way to the right, or as we go all the way to the left. The parent function is pretty basic, so we don't really have to worry about that, but this line can be crossed. I do want to emphasize that. The horizontal asymptote can be crossed. It only applies out on the right and left ends, like all the way out there. And what to look out for? How do we identify the horizontal asymptote from an equation? Well, you're going to compare the degree. You'll remember that that's like the highest power in a polynomial. We're going to compare the degree of the numerator versus the denominator. And there are 3 cases. I'm not going to go into those cases. If you need a little bit of help on rational functions, I'll post a link for a video that I have on rational functions specifically, and you can check that out at another time. But just know that we have to compare the top and bottom. If, by the way, the numerator degree is greater than the denominator degree by 1, then we're going to have something called a slant asymptote, which I'm also not going to get into. It doesn't really play a role in this problem. But what I mean by a slant asymptote is that there would be some kind of boundary line that's at a slant, as the name suggests. And perhaps there's also a vertical asymptote. And then the graph itself would kind of like bend in between those. See how it still approaches this boundary, but it's just not a horizontal boundary. It's like a slanted boundary. Again, not going to play a role in the problem that we have here, but it's good to know about that. And if you need to go and review your stuff with rational functions, feel free to do that. So the caveat to the vertical asymptote, here we go, is the hole. Sometimes these rational functions, they have a hole in them. It's not a boundary in the same way that a vertical asymptote is a boundary. It looks like the function's doing just fine and dandy, going along, and then all of a sudden there's just like an undefined spot, and then the graph continues. It's just a little blip. It's like a pixel missing from a picture, just a tiny little portion. And this happens whenever we have a common factor in the numerator and denominator, which could be equal to 0. It's very important. If those factors can't equal 0, then there's no threat of dividing 0 by 0. There's no problem with our fraction. Really, the idea is that if we're dividing 0 by itself, that's just completely indeterminate. We can't figure out what that is. We can't even say that it's approaching positive infinity or negative infinity. So it's not just undefined in the same way that a vertical asymptote is undefined. What to look out for here, a common pitfall here, is that people look for the denominator and they'll see a factor and say, okay, I'm going to set that equal to 0, bam, there's my vertical asymptote. But that's not always the case. You have to be patient. So before presuming that there's a vertical asymptote, you should always check to see if the factor is also present in the numerator somehow. You might not have the numerator in factored form, so it may not be obvious, but it's possible that there's a common factor in the numerator and denominator, so you shouldn't say that there's a vertical asymptote. You should say there's a hole in that case. All right, I think that gives the general breakdown of the features. Now we can take these features into account, because let's start off with this. It has no vertical asymptotes. What does that mean? Well, that means that the denominator is not just going to equal 0 with the numerator non-zero. So keep that in mind. There could be stuff in the bottom. Doesn't mean there can't be like an x in the bottom. It just means there can't be an expression which could equal to 0. So we'll more carefully look at that in a moment. It has a horizontal asymptote at y equals 2. Now I mentioned that there are 3 cases for determining what a horizontal asymptote is going to be. And one of those cases is when the numerator and denominator have the same degree. So this is going to be that exact case. We can say with certainty that the degrees are equal. Degrees are equal for, I'll just abbreviate, NUM and denom. I'm not spelling demon, don't worry, it's denom for denominator. And they're equal, but the ratio of those leading terms has to be equal to 2. That's what results in an asymptote of y equals 2. So we can just throw a 2 on the top over 1. That's all we have to do. It's very simple to impose that. Now, this third part is one of the more telling features. We have a hole at x equals 3. So what's the factor that's involved? I mentioned there has to be a common factor for there to be a hole, but I didn't really describe how to directly interpret the location of the hole with what the factor looks like. It's very simple. If x equals 3 causes a hole, that would be because x minus 3 is a common factor on top and bottom. Think about it. This would be a problem if x equals 3, right? If I try to plug in x equals 3, the top goes to 0 and the bottom goes to 0. So x minus 3 has to be the factor that we're looking at here. Let's go ahead and put that factor on the top and bottom. So yes, they would cancel when we simplify the function, but we got to know that that is there initially, because if we don't write it at all, we won't realize that there's a problem at x equals 3. If I just canceled it and didn't write it as part of the function, well then someone looking at this function wouldn't know that there's a hole at x equals 3. They'd have no reason to think that there's a hole. And I'll show you how to cancel the factor in a moment, but still preserve that restriction that x can't equal 3. And then we have this very important feature. It's undefined only at one point. What point do you think it's undefined at? Well, probably the hole that we just discussed. The hole is a blip. It's an undefined portion of the graph, kind of like I demonstrated here. So if there's a little blip at x equals 3, we don't know what the y value is, but we know that at x equals 3, there's a little blip. That has to be the undefined point. If it said there's more than one undefined point, okay, we might have more holes or more issues, but since they tell us that there's only one undefined point, and they also tell us that there's a hole, you kind of just put 2 and 2 together and say, well, that has to be the undefined point that they're talking about. So are we done? Because this looks like a really easy function. And you'll notice that I extended the fraction, suggesting like there's a little bit more to it, guys. Yeah, we're not done. Because if I were to simplify this and just call it 2, comma, x does not equal to 3, that would just be a straight line. And it would not have the correct horizontal asymptote. If it's just a straight line at 2, you can't really say it has a boundary or an asymptote at 2. Because the 2 suggests, the boundary or horizontal asymptote suggests that we're not going to reach that value. But if the function value is 2, we're always at that value. So what I'm saying is we need to jazz this up a little bit. We need a little more flavor on the top and bottom, but we need to preserve 2 things. We need to preserve that there are no vertical asymptotes, which means the denominator cannot equal 0. So we can throw some factors in the denominator. They just can't be factors that equal to 0. And you might be thinking, what kind of factor is that? Because no matter what I put down here, x plus 4, right? That can equal 0 if x is negative 4. X plus 7, that can equal 0 if x is negative 7. X minus 2, x minus a half. You can throw fractions or whole numbers or negative numbers in there, and you can always make it 0, right? Well, if you think carefully about what kind of factors we can throw in here, how about a squared factor? How about like x squared plus 4? That will never equal 0. Think about it. X squared. Meaning any negative number becomes positive, and any positive number stays positive. And if we have a 0 and square it, that's okay because we're going to add 4. It's x squared plus 4. So the denominator is never going to equal 0 because we carefully selected an option for x squared plus 4. You can pick whatever option. You put x squared plus 5, x squared plus 2, x squared plus 0.1. I don't really care. You can even put x squared. You can't just put x squared, actually, because then x wouldn't be able to be 0. But x squared plus anything, literally plus anything. You don't want minus. If you put x squared minus something, you can obviously get 0 from that. But if you put x squared plus anything, plus 9, plus whatever, you will not get 0. So we have to preserve the horizontal asymptote as well, which means the degrees need to remain equal. So if I'm going to put an x squared thing in the bottom, I have to also put an x squared thing on the top. And I don't have the same restriction on the top where it can't equal 0. I could put x squared minus 1 if I wanted to. But I just decided to make it simple, x squared plus 1. When you guys solve this, you could have put whatever you like. And so our simplified version of this equation is going to be a little different looking. It's still going to cancel the x minus 3's. But now we're going to have x squared plus 1 over x squared plus 4. And then let's mention, otherwise people wouldn't know, that x cannot equal 3. And this would be a perfectly valid equation that satisfies all of those conditions. Okay? Well, I encourage you to look at the graph on Desmos. In fact, I encourage it so much that I took a screenshot of it, and I'm going to show it to you now. Here is the same function that I plugged in. I don't have to tell Desmos that x can't equal 3. It's a calculator, so it can work that out on its own. But I want you to look at the graph because it has interesting features, right? We mentioned that it has no vertical asymptotes, and you'll see that it has no vertical boundaries at all. It does have this horizontal boundary at y equals 2. And that was one of the conditions that we had to meet when we were creating this equation. And it does have a hole. I'm doing really bad at drawing these like dotted lines, but you get the idea. And it does have a hole at x equals 3. See, I purposely clicked on this spot, and it tells me that it's undefined. That's the one undefined point, the only undefined point. And you might be interested to see the fact that it's like looks upside down. So what's going on with that? Well, in order to do a further discussion about this problem, let's consider a different form of the equation. Now, it's the same ingredients, you might call it. It's the same starting point. I am going to use this, which I just constructed. However, I'm going to represent it differently. What do I mean by that? I'm going to distribute the 2, but that's not all. What I'm going to do next is I'm actually going to perform the polynomial division. Do you guys remember this? Polynomial division. There's long division, synthetic division. We're going to be carrying out long division. 2x squared plus 2 over x squared plus 4. Now, if you need a lesson on long division, maybe it's been a while, go ahead and review it. But I think this one is short enough that it's not going to cause too much confusion. You'll probably remember some things. So we got to ask the front runner, x squared, how are you going to turn into the front runner, 2x squared? And of course, we have to multiply. That's going to be multiplying by 2. So here we have 2x squared. We multiply that. And we multiply the plus 4. 2 times 4 is 8, obviously. And we subtract these off. We're subtracting a multiple of x squared plus 4. And that leaves us with negative 6. Well, negative 6 is not even a big enough front runner for x squared to turn into that. So we're pretty much done. This is our, do you remember? This is our remainder. Okay. So that means that our division here, 2x squared plus 2 over x squared plus 4, this really just equals 2 minus 6 over x squared plus 4. That's how we express the remainder. Right? Like if you were dividing, I don't know, 45 by 7, you would take 6 7s out, and you would be left with 3. So you would say 6 plus 3 7s. It's kind of like what we're doing here. You're saying 2 whole x squared plus 4s, but then minus 6 divided by x squared plus 4. And why do I want you to look at this equation in a different format? Because you might kind of connect the graph a little bit more. It might register better if you realize that this is a graph which is shifted up by 2. It's like a vertical shift. And then this is really the rational part. So what do we notice about this? It's flipped. It's also not in the form of like 1 over x or a number over x. It's in the form of a number over x squared. And that has this kind of bell curve shape to it. But because of the negative, it's flipped. So it's almost as if this 2 is like a lifted string, and there's this like weight hanging off of it. As far as describing like the shape of the graph, it's kind of an upside down bell curve. It's just like a little dip, right? Actually, it kind of looks a lot like what you might see in like a mattress commercial for like selling beds and stuff. It's kind of funny. So it's an upside down bell curve. The typical shape of 1 over x squared plus 1 or something like that, x squared plus anything, remember that's going to cause there to not be a vertical asymptote. So that's why there's not this break. You're going to see this bell curve kind of shape. Oops. And the asymptote, the horizontal asymptote, would normally be at 0, the floor, but we had this 2 there, this plus 2, which lifted everything up by 2, and then we flipped the bell curve down. Yeah, so I think that's enough blab out of me on this one. I hope you had the opportunity to try this for yourself, and you're probably a little bit better equipped to tackle rational functions. So I'll see you guys next time.